So the reason that it's weird because space-time itself doesn't actually take vector spaces like as a structure. It's more complicated than that. But what happens is that when you take a chart of a manifold of space-time, that ends up being a vector space structure. And so that's why we take a look at it. And so the intuitive way of seeing that space-time isn't a vector space is by saying like 5 times Paris plus Vienna or something.
But does that mean like, so if you equip the real world, like if you define an origin or something and give it a basis, does that mean that you can say 5 times Paris and like whatever? Like,
but what you've effectively done by equipping it with an origin is you chose a chart.
Oh, so our chart is a vector space.
I think it's a bit more complicated than that, but that's the intuition in my head. Like, I think it's more complicated, but I'm not sure. Like, this is future topics I still haven't went over. And so that's why we care about vector spaces, even though it's not like directly applicable. And they also just end up being useful in general, I guess.
Yeah, like understanding. I guess it's also useful to understand what space-time is not, I guess.
Yeah, I guess so, yeah.
Right.
And I guess it's also useful where you can learn what a tensor is without having to deal with all the complexities of space-time and like manifolds and whatever.
Yeah.
It's like a training ground, I guess.
Okay, that makes sense.
All right. Next up, I've niched with vector spaces.
Yeah. Okay. So looking at my notes, I noticed that I wrote a vector space, and then I crossed it out, and then I wrote a real vector space.
Yeah.
And I don't remember why I did that, but anyway, so a vector space is like a tuple of 3 things. So you've got a set, and then some notion of addition, which takes 2 elements of that set, and then returns a new element, right? And it has something called S multiplication, which intuitively you just think of scalar multiplication. You take a real number and you use this special multiplication. And so you multiply this real number by an element of this vector of this set, and then you get a new element of the set. So, and then there's the whole, so there's the whole like properties or the axioms of vector spaces, which to me kind of seem a little, like they do seem intuitive, right? So like, so the first 4 are like talking about addition. So when you add 2 elements, the addition of 2 elements of this set we call V are commutative. The addition of any addition of any number of elements of the set is associative. So they're commutative, associative, and there's a neutral element, 0. You know, basically what 0 does in addition for real numbers, it just when you add it, like nothing happens. And then there's an inverse, which is basically like a negative, so that you get this neutral element 0, or whatever you define as 0 for this vector space. And then there's another kind of associative, where you take like a scalar, so basically a real number. So basically associativity for like this multiplication. And then there's 2 distributive properties. Again involving 2 scalars. Actually, no. So the first one involves 2 scalars, and the second one involves 2 vectors. And then there's a unitary operation where you take. Hold on.
You multiply by 1.
You multiply 1 and then nothing happens. Yeah. I mean, I guess it would be better to explain it if I drew something, but I think like, we kind of get it. Just properties, axioms of vector spaces.
So what's a vector?
A vector is an element of the vector space, just as how an open set is nothing more than an element of the or a member of the topology. It's the exact same thing. You define a vector space first, and then you define a vector. Similar, like you define a topology first, and then you define an open set. They're basically just like that.
If I point like this, is it a vector? Like this arrow?
Yeah, it might be, depending on like if we have like I need to have some notion of addition and then S multiplication.
Okay, yeah.
I guess. And then I need to be able to like check that all of the 8 axioms have been satisfied. But to do that, I need like, yeah, you need a set, addition, and S multiplication to be defined.
Okay, makes sense. Jacob, how about you give an example of a vector space and how you'd build one?
I don't know how you'd build one, but I can give an example.
Sure.
An example of a vector space is okay. So to give a very, very simple example, R3 equipped with the standard plus operator. To give a trickier one, there's a if you you know what a Fourier series is by any chance?
Yep.
So
Do you know what it is or no?
No.
Okay, then we shouldn't use it.
I don't know if I have any other good examples.
I mean, R3 is a good one.
Sure. R3 equipped with element-wise addition and also a scalar multiplication. Yeah, I mean that's a very simple vector space. But I'm trying to think of a vector space that will stretch our understanding of vector spaces.
I mean, the one he gave in the lecture, I found kind of interesting. Of like a set of polynomials, basically. Which, or was it that? Yeah. Which I found interesting because it's sort of like. Wait 1 second. Yeah, I found it because like I'm still new to the idea of like thinking of like functions as vectors, which is cool because like you don't, because functions aren't necessarily like an arrow in space. And I've heard people say, oh, you could just like think of a function as like a vector with infinitely many like coordinates, right?
Okay.
But I mean, technically, like, sure, you could think of it as like having infinitely many components, but in reality, it satisfies the axioms. That in itself just makes it a vector.
And you can kind of think of it similarly. The way I think of it is, well, there's two ways I guess I think of it. One is any function, if you discretize it, you can turn it into a list of points. And then the fun thing is if you choose any set of functions that are orthogonal to each other and spanning the space, you can take a linear combination of other functions and do all kinds of vectory things. You can call them basis functions, just like you have basis vectors. So one word that didn't get discussed a lot, guys, was linear combination. And that was like essential from the beginning of my linear algebra understanding. It's just, and so David, tell me if I'm wrong to bring it up right here.
With linear combination. By the way, there's like some sort of rattle on your end.
Yeah, I know. I've got to mute it. I'm going to be back soon.
Okay, cool. Linear combination. I don't know. I feel it's implicitly defined with the axioms of vector spaces. A side effect ends up being that you can take linear combinations of, and
I mean,
I don't know.
A linear combination is basically just the addition of vectors, right? So
of basis vectors.
Is it?
It doesn't have to be a basis vectors. You can take any vectors. No. You can take any vectors and take a linear combination of them and produce other vectors.
Wait a sec, but that a linear combination is literally just addition of vectors together with maybe a little bit of S multiplication, scalar multiplication.
Right. Yes. Yeah. So with just that, you've got addition, you've got scalar multiplication. That's a linear combination, I guess.
Right. And so the motivating factor for making this whole vector space thing, like in terms of answering the question, why do we bother with vector spaces? For me, linear combinations is the first explanation I got of this. It's like, hey, you can take linear combinations of existing things and you can make other vectors out of it.
Yeah. Well, I think I agree with you that that is probably the nicest property of vector spaces. The fact that you can do like this triangulation or whatever.
Wait, one second. What is you mentioned like having functions that are orthogonal to each other? What is that? How do you have like orthogonality in functions? Like, how do you check that?
You use a dot product, which I don't know if is too ahead of us.
Well, how do you take the dot product of a function though? Because like
you do
I mean-
literally the same way you do normal. You consider that you discretize the function, and then you do element-wise dot producting, and then it's when you take the project. It's basically the way you define projection, which is basically the shadow that one vector casts on the other. Ultimately, becomes like the dot product divided by the magnitude of the thing that the shadow is being cast on. So that's not so that's basically making it into a unit vector. And you do the exact same operation on a function. Is you take the dot product of two discretized functions, which are like asymptotically infinitely dimensional, and then you divide by the magnitude of the target function.
Wait, how do you discretize a function?
Oh, you just say like the first, instead of saying sine x is this big continuous thing, you just say, okay, sine x at point 1, sine x at point 2, sine x at point 3. Those are going to be the first, second, third element of a really long vector.
Well, wouldn't you then have like uncountably infinite points?
Yeah, this is more of like, I think if you wanted to get super rigorous about it, there might be some complaints, but and this is a case where discrete math maps pretty well onto continuous math, where you could just say, you just assume that there's countably infinite points for all your ordinary intuitions.
Okay.
In any case, I feel, yeah, that is a nice property, or probably the main, like that's why it's called linear algebra. It's because you can take linear combinations of the elements and you're guaranteed that the resulting combination is also an element. But yeah, let's move on to linear maps, which is I'll start off with linear maps. Is that cool? Yeah. Cool.
Sure.
So in my brain, linear maps means an abstract thing. Like it's an abstract concept in the same way that vector spaces can be abstract. But if I was going down to the specific intuition level, I would translate linear maps to be equal to matrix, because a matrix is a linear map. But obviously you can have linear maps that aren't matrices, but it's kind of like the whole idea that a square is a rectangle, but a rectangle is not a square, like overlapping circles of Venn diagrams.
I mean, I mean, because to me, like in itself, like the definition of a linear map is sort of I mean, because like, actually, no, wait, just continue.
Yeah. So the idea with a linear map is that it preserves structure, and it's not bijective, that's the wrong word, but it's like it's the idea of like a bijection, but that preserves structure.
And structure kind of like, meaning the structure of those vector axioms?
Yes, that preserves the vector axioms, yes. So in the same way that with topology, we had homomorphisms between topological spaces, and they're like, okay, they're kind of equivalent. In this case, you're kind of doing a similar thing. So pretend that you were working with the vectors, like the physics vectors that we're used to. What you can do is you can have a vector, and then you can multiply that vector by a matrix. And a matrix is a linear transform. So it'll take your vector and it'll transform it to another vector. But the addition and the multiplication properties are preserved, like the axioms of the vector spaces are preserved. And so that's why it plays nicely, I guess, is what you could say. So you can come up, yeah.
Homomorphism versus homeomorphism, or versus homeomorphic. Were we dealing with homeo?
Oh yeah.
Was homomorphisms a thing in topology, or was it only homeomorphic?
I forgot which one was which.
Let
Homeo.
me do some searching up here.
Where did we see the word homeo before homeomorphism?
Homeotropic. There's homeotropic equivalence or something versus.
Okay, I see. I think the difference is that homeomorphic is specifically for topological spaces, but homomorphisms are for all kinds of spaces.
And then there's another thing which is homotopy equivalence.
That's beyond. I don't know. Like, I don't know what it is. So
Okay.
like I don't know. I think the way I think of it in my brain is you have a really big circle called homomorphisms. And then in that circle, you have all different kinds of homomorphisms. So you have like homeomorphisms for topological spaces. You have linear maps for vector spaces. You have whatever the other one is for other kinds of spaces. But the big circle is homomorphisms.
Okay.
Yeah.
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 Okay, cool.
And I just wanted to add, like, so I think there are like two conditions for a linear map. And the first one is basically like, so if you have like, so you have like a linear map phi, right? If you first take a linear combination of two vectors and then apply the map, that's the same thing as applying the map to each of them first and then taking a linear combination.
Yeah.
And the second condition is if you take a scalar multiplied by, so if you scale a vector and then perform the map, that's the same as performing the map first and then scaling it by the same constant.
In my head, that just means that the structure is preserved, though, like the axioms of vector spaces. That to me is like the direct meaning, I guess.
Yeah.
But yeah, essentially. And then there's the idea that if you take a linear map from one to another, and then a linear map from this guy to this guy, the map from the first guy to the third guy will also be linear. But that's been like a consistent theme for a long time now.
Yeah. Composition of linear maps is linear. And that's kind of why like matrix multiplication results in another matrix.
Yeah,
because
exactly.
Yeah, because like you've got because it's a composition of two linear maps.
Mm-hmm.
I guess it's important to note with matrices though that you might get the wrong size. So it might not be
sure?
that you can compose. I mean, if you multiply matrices of one size or another, it can change, and it's not. It's like you have to. What I just wanted to add detail to the comment.
Oh yeah.
Okay. But I think
the new one would still be linear though, like even if it's like a different size, right?
Sure, totally. But you can't just add them up blithely.
True.
Sure, you can't, because the idea of a linear map is that it's structure preserving. So maybe it's impossible to map from a 2x2 matrix to a 3x3 matrix because it's just not structure preserving.
I think there was like, you can like, there was something like if like the number of columns is equal to the number of columns of one of the matrices is equal to the number of rows of the second matrix, then you can do multiplication.
Oh yeah. You're right. Shit, yeah. Okay, I
Yeah,
guess.
So
I guess
one way you can think of it is you can multiply. So you know how if you take a what is it, a column vector and you multiply it by a row vector, it becomes a scalar. Equivalently, and this is the or one second. Yeah, you take a row vector. One second. I'm just being very you take a row vector times a column vector and it becomes a scalar. And then you take the opposite. You take a column vector and you multiply it by a row vector. It will become a square 2x2 matrix.
Really?
Yeah. Yes, definitely 100%.
Okay, Yeah, it's been so long time since I did linear algebra.
Okay. Yeah, but absolutely does. There's absolutely a property like that. And the word that you might come up at some point is the inner product and the outer product.
Yeah. So like If you
Right.
take like, a bra and a ket, you get like a scalar. And
Oh.
if you take like a ket and a bra, you get like a matrix.
Mr. Quantum Mechanics here. Yeah.
Yeah, I mean, hey, quantum mafia.
I guess, yeah, fair point.
Mm.
All right. Next topic is the most crucial one, very small but crazy, and it's vector space of homomorphisms. Jacob, you want to try taking this one?
Yeah, sure. I'll take it a shot. The okay, so looking at my notes on this topic, one second. So the definition homomorphism is a structure preserving map between two algebraic structures of the same type, such as two groups, two rings, or two vector spaces. Homomorphisms of vector spaces are also called linear maps, and their study is the object of linear algebra. And the definition in our text, which I tried to translate into literal English, is the homomorphism between V and W is the set of all linear maps between V and W. Is that wrong?
Seems accurate.
And so would you say the homomorphism between V and W, or how do I use it in a sentence? Is my question.
Oh. Like, is hom of VW the homomorphism?
Because it's a set. It's a set of everything. So I'd say it would be there's only one homomorphism, right?
I disagree. If I tell you that the identity matrix is a homomorphism, or how about this? Here's a sentence. The identity matrix is a homomorphism from a vector space R to, or whatever your space is, to whatever your space is.
No, I'd say it says then the homomorphism is defined as a set consisting of elements phi, where those elements phi are linear maps from V to W. And does it mean all elements phi or just any elements phi? And I don't know if you'd say a homomorphism between.
I think
the question is.
Okay, I see. I think this would be named the vector space of homomorphisms is defined as the set of maps.
The vector space of homomorphisms.
Yes, because there's a lot of possible.
But wait, is it even a vector space of homomorphisms?
Oh, shit. The set. I guess it's a set first, but later on you can make it into a vector space.
Okay, the set of homomorphisms between V and W is the set of all linear maps between V and W. And let me see. I think I had one more comment on that, which is
did you have a
okay. That's all I've got. That's all I have to say on homomorphisms. Let me repeat that one more time. So to use this in a sentence, the set of homomorphisms between V and W is the set of all linear maps between V and W. Now, to me, I don't understand how the word homomorphism is any different than linear map.
Linear maps, homomorphisms. I think it's the same.
Homomorphisms of vector spaces are called linear maps. That's all it is.
I think the difference
for vector
is that
spaces, they are the same.
Yes, exactly. Wait, question of Nish, by the way. It looks like a few.
Yeah, hold on. So are you saying that a homomorphism of a vector space is called a linear map? But then there are other kinds of homomorphisms that are not linear maps.
Yeah.
And those are the ones that don't apply to vector spaces. Is that basically the gist of it?
Yeah.
Okay.
Like, as an example, a homomorphism of a topology is a homeomorphism.
Okay. Wait, what were homeomorphisms?
Wait. I don't. Wait. That's not even. I'm actually curious there, because that would seem like why. So a homeomorphism is a new special. Why don't we just call it a homomorphism? So homomorphism of a topology is a homeomorphism. That we created a special word for it. So the word homeomorphism is sort of the analog of the word linear map. Is that right?
Yes, but for topologies instead of vector spaces.
Oh, that's cool. Okay.
Avnish,
No, I'm just like I just opened up like Wikipedia.
that's cool.
Homeomorphism, continuous function between topological spaces that has a continuous. Oh, okay, wait. I think I remember this. Yeah. Yeah, I think I remember this. Okay, cool.
So it's like linear map equals homeomorphism, but one of them is for vector spaces and one of them is for topology. That's what I feel.
Mhm.
Cool. Anything else you want me to cover on that? Is this very short definition?
Do you want to give an example?
Sure. A homeomorphism between the let me think of a simple example.
Vector and vector.
Yeah, I'm just giving a very let me do it on my own.
Sure.
I want to do it on my own.
Sure. Cool.
Let's do another one. Okay, so here's one. Projection onto the x-axis from a if you have a vector space ij, like whatever R2 is, and you've got vectors ij or whatever that are little basis vectors, the operation of projection onto the x-axis is a linear map, aka a homomorphism of a vector space. And what that looks like is the identity matrix with the second one turned to a 0.
So wait a sec. You said that projection onto the x-axis is what? Is it a homomorphism or is it a vector space of homomorphisms?
It's a linear map and it's a homomorphism and it's a homomorphism.
Okay.
And
So I guess an element of
Of the vector space.
Yeah.
Yeah.
So it's an element of the home of R2 to R2 basically.
R2 to R1 because you're projecting onto an axis.
It's depending on how you do it, it could be an R2 to R2. So.
Okay, yeah, fair point. If you wanted to.
Wait, what do you mean?
I guess.
Because if you did it and you could do a projection operation that truly reduces it to a scalar, or you could just leave the second two-dimensional object very just being pedantic.
Yeah, it's true. Yeah, like that. Yeah, this is being put in. So that's an example of a homomorphism. Do you have an example of a vector space of homomorphisms?
How about the set of all, I mean, this is a stupid one, but I mean, I don't know if it's a stupid one. I think the set of all 2x2 matrices with real components with real elements is a set of homeomorphisms or homomorphisms, right?
Yeah, takes from vector to vector.
And then also, and you could also say a set of also all the rotation matrices. That's another. Would you call that set of homomorphisms?
I guess if you're being very loose there, like if you say,
no, not loose at all. It's just a subset. Go ahead.
Yeah. Like you're right, the subset. Yeah. Like if you said, I choose the subset of all matrices that cause a rotation, like there's an infinite amount of results, right? But yeah, I guess it is technically.
When you say a rotation matrix, do you mean matrix? Do you mean like just those that have the form like I don't know, was it cosine, sine, negative sine?
Yeah.
Like do you mean just those for like all of the possible angles?
Right. So just to select all the values exactly.
Wait a sec, but that's a set of homomorphisms. If you wanted a vector space of homomorphisms, you'd have to define addition and multiplication on the resulting, like on those matrices, for example.
So how do we define addition?
I mean, addition is easy enough. You just add the components together of a matrix, and then S multiplication. You just
again,
like the scaling a matrix basically. So it's basically just like addition and multiplication for like any matrix could work. As
At what point were we talking about scaling? And I just don't remember the topic of under what circumstance would you care about a vector space of homomorphisms? That wasn't in the definition I just gave.
At what point would you care about that?
Yeah, but the lecture didn't talk about vector spaces of homomorphisms, did it?
I think so. Yeah, it talks
I mean,
about
it
it
was one of
basically
the-
everywhere.
It was one of the topics. Like, remember Hom VW? And then there was like,
No, but Jacob, you're talking about application of this concept, right?
It didn't say Hom VW didn't say it was a vector space, did it? Maybe I just missed something.
what Hom VW initially is a set, and then it becomes a vector space. Like if you define, they said that, so like you can construct addition and scalar multiplication.
Yeah.
And
Okay.
How do they do addition?
They define it. Like, yeah, they define addition.
Yes,
Oh,
yeah, I
okay.
see it. Yeah, 3.3. Okay,
Yeah.
I see it.
Yeah.
Exactly that.
And they gave an example of like the derivative operator as a linear map, like a member of
Yeah.
Hom PP, and I was like, ugh.
Did you get that or no?
I think I did though, because I don't really know calculus, but like I understand
Mm.
enough about it to understand this, I think. So
Mhm.
actually, wait, hold on. Let me just like check if I get it.
It's very interesting
Yeah,
what
so-
they say.
So the derivative operator is a linear map. Okay. Which means it's an element of Hom PP, and P was so P in the lecture was like
What
the
is
set of all
Hom PP?
polynomials. So first of all, P was the set of polynomials.
Yeah.
Right? Yeah.
Agreed.
And then
So Hom PP means
so the set of all linear maps from one polynomial to another.
Yeah.
Okay. And then the derivative operator is one of them, because it takes like a polynomial and then spits out another one, which is usually like, you apply like that rule where you like hop down the exponent and stuff.
Yep. What about
Yeah, and then-
addition?
Addition. How do you do addition?
Does that count? Or how about negation? Negative. You just add a negative in front of the polynomial.
Yeah, and then if you add both polynomials, it'll end up being 0. Right? If you add like a polynomial and then like the polynomial times -1.
I think what I'm
Right.
saying is
Or what are you-
that is negative, the negative operator, a part of Hom PP?
Oh.
Because it says derivative is a part of Hom PP. That one we can agree on.
I think it is, because like, I mean,
I think
why wouldn't it?
I think
yeah.
the reason why it wouldn't would be if it's not linear, which it might not be. I don't know.
Wait, hold on. Okay, wait. We should probably be able to test this pretty easily. So, hold on. Actually, can I just like write real? Oh,
Yeah.
never mind. I can't. It's almost 1%. Whoops. That's gonna leave soon.
Oh well.
Okay, wait. Actually, I can just have. So like, if we have like, or I'm not gonna type this. So like, let's say we have a polynomial 2x squared plus 3. I don't know.
Sure.
Right?
You add a negative, becomes negative 2x.
And then
negative
acting
3.
linear. So first we need 2 polynomials. So let's say 2x squared plus 3, and then 5x cubed minus 1. Hold on.
Sure.
Let me just like put that in
The
equation.
whiteboards.
2x squared
Oh yeah, good idea, chats. That's better.
plus 3 is one of them. And then 5x cubed. Let's do minus 3x. Okay, and then those are our polynomials. And then to
Is
check if
it-
they're linear. So multiplying. So does multiplying? So would adding these up and then multiplying by -1. So if we add them up and multiply by -1, we get -5x cubed minus 2x squared plus 3x minus 3, right? So
Yeah. First you have to add them up and then add the negative. And then
okay.
yeah.
Yeah, so you add them up, you would get 5x cubed plus 2x squared minus 3x plus 3.
Yeah.
And then you add the negatives, so you get this,
Yes.
right? And then is that the same thing as, so applying the negative to each of them first and then adding them up? And I think, yeah, it is.
Okay, so it passes check mark for that.
It passes the first one. And the second one is when you multiply by a scalar. So multiply by, okay, so for the next one, let's just start with, I'm just going to add a line and then 2x squared plus 3, right? So you start with this, and then our scalar is, I don't know, 4, right? So the first test, okay, so this seems kind of obvious, but like the first test is multiply by 4 first, right? So you get 8x squared plus 12.
And then negative.
And then add a negative. And then that's the same thing as adding the negative first and then multiplying by 4. Yeah, it's actually pretty simple exercise.
Okay, cool.
So the negative, multiplying by -1 is linear. And so it's a part of
Awesome.
HomPP.
Jacob, any questions?
I'm looking back at the example earlier with the consider a set of polynomials of fixed degree.
Mhm.
And
fixed degree?
Look at 3.1, the example.
I didn't label them with numbers.
Oh, it's just in the notes.
Oh.
Yeah, a fixed degree. Yeah.
Yeah, and so I'm realizing now that as you gave the example, I actually don't understand the example in 3.1, because why would you say P? So P is a set of functions that map from elements of the interval -1 to 1, and then to all real numbers. Why would we restrict? And what I'm saying is that x can only range from -1 to 1, non-inclusive, right? And so why are they? That's not the set of polynomials of fixed degree. That like x could be anything in the polynomial, right? Why are they restricting that?
Yeah, I think it's still the set of polynomials of fixed degree, but with a restricted domain.
Okay, I said a set, not d set. Okay. And then the point is that so the set of polynomials of fixed degree in general is a vector space, and then the set of polynomials, then this particular set of polynomials of fixed degree is also a vector space. Is that valid, by the way?
I think so.
Okay. Anyway, return. That was my only. Okay, understood.
Yeah.
Please continue, guys.
I think the reason why they restricted the domain is just for simplicity reasons, like to not have to deal with weird things, maybe.
Wait, actually, yeah, like what weird things could arise if you just went from R to R? Like, I don't see why that would be a problem. Like restricting, like why would we need to restrict the domain?
I'm not sure. Maybe they just did it to be fancy and to see, like, to confuse people. I don't know.
Yeah.
Like in a good way. Like good.
I'm noticing, like, because it is an open interval. So
yes.
Does that mean something? As a nod to topology or continuity or something like that?
Yeah, because in this case we haven't introduced a topology, so we don't care about open intervals, closed intervals.
Or do we just like assume the standard? I mean, do we need to? Not really.
No. We're not talking about continuity. Yeah.
Right. Yeah.
And by the way, in that example, the plus operator is the composition operator. No, it's not the composition operator. Never mind.
Which plus?
Never mind. Okay. And in the example, it said, I was trying to understand it defines an operation P plus Q of X, which is kind of a weird operation, right, guys? Like that. Why would you?
Oh yeah.
I don't understand. I would not. That was a bizarre operation, and then it defines that as P of X plus Q of X. But when I don't like that's really arbitrary. Like why? Under what circumstance would you? Is there any example, like even with derivatives or whatever,
well, I
you
think
don't define
you mean like the part where it
like
says
that.
like P and then the circle plus Q is a map of P circle Q of X, which is equal to P of X plus Q of X. Like, do you mean that part?
Yeah. I just don't understand why they would have chosen that. Like, what's an intuitive example of anything that you'd ever cause to interact that way in real functions, like in functions that I may have encountered in my life?
I'm a little bit lost here. Which line are you guys? I'm trying to find it.
I'm on section 3.1 underneath example, consider a set of polynomials of fixed degree.
And then the first line or the second line?
It says with the circled plus is
a
function mapping from P by P, like a two-dimensional P to a single-dimensional polynomial. And I'm just trying to understand, like what would it even mean to have, like, is there any situation in any part of math that I may have come across where it would make sense to define a plus operation on two functions like that, or at all?
Yes, I think so. So the way they're defining this plus operator, I think, and I think that because I was like watching today, to review, I watched 3 Blue 1 Brown's video on abstract vector
nice.
spaces.
Yeah.
And then basically
Abstract what?
Abstract vector spaces. So it's the
Okay.
last video in the linear algebra series.
Yeah.
I basically said like you can define adding two functions as like for every, so like let's say you have one function that looks like that and the other function that looks like, I don't know, like that or whatever. So like you could define adding two functions as at taking every point, add their outputs.
Yeah.
So so like let's say f of x equals x squared and then g of x equals x cubed. You could define f circle plus g as x squared plus x cubed. So
is that any different than composition? Hang on, let me think about that.
I think it's the same thing as composition.
You say that again.
No.
Say it one more time, Avnish.
Okay, so like let's say you have so you
wait, composition. Sorry, I made a mistake.
Yeah,
not composition.
Composition is like after, right? So like let's say you have f of x is equal to x squared, and then g of x equals x cubed.
Yep.
You could have f and then circle plus g of x. You could define, wait, hold on. One second. So you could define f and then that parentheses plus, I'm just going to call it the circle plus. So f plus g of x is like x cubed, which is a real number, and then x plus x squared, which is a real number. So we're defining the addition of functions as at each input, add the outputs. So like f of 2, for example, is 2 squared, which is 4. And then g of 2 is 2 cubed, which is 8. So then you could define f plus g of 2 as 4 plus 8.
Oh, whoa. You know, matrices all behave this way. Don't they?
I think so.
Okay, if that's true, that's all the answer I need here in terms of motivation for this.
So when you add two matrices, you just like add up each corresponding
element-wise,
right?
Yeah.
Does that work? I mean, I don't know linear algebra that well, so
I think it works. David?
Yep. I was listening to you guys, sorry.
No, it's okay. I was just curious if no, it's all good. I was just curious to ask if you had I thought all matrices actually behave this way. That's why it's not weird. Is my guess right here.
We're like adding two matrices is the same as adding up the results of multiplying those matrices by any vector.
Yeah.
Yep. Okay. That's all I needed to do. So my point about that is that's why you'd consider basically, and you can consider matrices to be operators, and then you can add up these operators and they have these compositional qualities, these linear compositional qualities. And that means you have a vector space of operators. And actually that's going to get me to my other question about, I didn't understand the concept of a gradient in the context of, let's just keep going and we'll get there. But go ahead.
Gradient as a covector. But yeah, let's get to that.
We'll have to do. I've got some covector questions, but go ahead, guys.
Dual vector spaces.
Oh,
anybody want to take this one? I can try explaining it. Or
sure,
I can try too.
Sure, Jacob, go ahead.
Yeah. So okay, I have a definition and a question. Okay, so I looked up dual vector space separately, but also firstly their definition is defined as the vector space that goes from wherever your vector space, or it's a linear map that goes from any vector in your space to single digit R. Is that right?
I think you're missing
R1.
the set of maps, right?
It's a set of all linear maps between. It's the set of all linear. Well, not. I guess. Yeah, I think it's the set of all linear maps between your vector vectors in your vector space and just R1. Is that right? Is it R1?
Yep.
Yeah. And like R1 equipped with like elementary school addition and multiplication, I guess.
Yes.
So
Yes.
we're making R1 a vector space, basically.
Yep.
Not
Yep.
just a
And
set.
so, and so an example of this is, let's consider a row vector. Let's consider a bunch of 1 by 2 row vectors. Okay.
Avnish, you know what a row vector is?
Yes. 1 by 2. So 1 by 2 would mean like 1 row, 2 components.
Yeah.
Yep, that's right. And that's like a bra in quantum, right?
Yeah.
Yeah.
And then all the kets, the 2 by 1, the 2 tall, 1 wide.
I think I see where this is going. Yeah.
All those things are called all those the set of all those things is the dual vector space, because when you multiply them, it takes you to one element things. Is that right, David?
Wait. The set of
all
set of
kets.
all
If you got the set of bras, the set of kets is the dual vector space.
I think you start off with the set of kets, which is V in this case, and you ask yourself the question, what can I put in front of this ket that will turn the result into a real number?
Yeah, because I'm thinking like if you start with bras, because like if you, well, actually, because like the order matters, right? Like that's what I'm just thinking. That if you start with a row vector and then put a column vector on the left side, then it's like, then it's a matrix. It's not a real number. So like, wait, so what's the correct way to say it? Like, which way is the correct order so that we end up with a
Take it
with a
take it
real
away,
number?
David.
It says, well, if you look here, it says if a vector space. So it starts off, you need to start off with the vector space to have a dual vector space. So you start off by defining a ket as a vector space, and then you get the associated row vector.
I don't understand why the order matter. Why we have restrictions on order here.
Well, if you go ket first, then bra, then you're going to get a matrix, which is not a real number.
Okay. But I mean, hang on. Maybe I just need to review these notes. Hang on.
Wait, well, because like I'm thinking like one way you might get outer well, what if you're talking about like, because actually not, because like doesn't duality go both ways? Like what if you say like what if you say like you start with the row vectors,
yeah,
and then you say put the column vectors on this side, and that's your map.
Yeah, you could do that, yeah.
Right, because like, so
I feel like it's abstract, like where you put it. In theory, we should really be putting brackets around everything.
Yeah, because things like this is all like assuming that you've defined an inner product, which is not like necessarily already implied by the vector space. Because like I'm pretty sure inner products are additional structure, aren't they?
Yeah, but we don't have inner products. It's called a Hilbert space if you have inner products. You have, it's called a Hilbert space.
Yeah, exactly. So like a Hilbert space, like because like a Hilbert space is just a vector space with an inner product defined. So like, yeah, so we have to define the inner product first, and then I guess like if we do that, that would kind of resolve the confusion about order, I guess.
I don't see how inner products have anything to do with anything.
Yeah, because like inner product is what results in a real number. So
well, I guess with this dual vector space or whatever. So tell me, if I have a row vector, would you call? Here's a question. If I've got a row vector, what you'd call the column vector of equivalent length the covector. Is that correct?
I don't know.
And
I feel
vice
like that's
versa.
what it
The
should
question
be.
is vice versa. And then vice versa, I think, is also true, right? If you have
Yeah,
a set of bunch of column vectors and the covectors set of row vectors, because the order, I don't know, the order defined. Yeah.
Yeah, I feel like it should be that case where like the covector of the row vector is a column and the covector of a column is a row.
Oh, sorry.
Like I feel like
Is
that's
okay
how
if
it
I finish
should
this,
be.
by the way? Yeah. I think if you say I think if you say I choose this row vector to be a vector, then the dual is the column vector, and that's the
Wait, but the dual is a
So
set of
not
all linear maps though, or the dual vector space. Oh wait, never mind. And so we're saying like first of all, like what we're talking about right now is one of the covectors of a dual vector space, right? Or like one of the linear maps.
yes, when we're talking about a covector, yeah.
So okay, so can you explain how the gradient is a covector? Because the gradient of a function takes like a 3 vector. You take the gradient of that, you still get a 3 vector.
First of all, what's a gradient? I don't really know what that is.
Gradient
A
descent.
directional derivative. A gradient is a directional derivative. It looks like an upside down triangle operator, or it's a specifically it's a specific directional derivative. If you want to go for it, I can. You probably have a cleaner definition than I do, David. Go ahead.
I think it's not important to go over if you haven't seen it before, which I presume you haven't.
I mean, I've seen gradient. I know what gradient descent is, I think.
Yeah.
It's very similar. There's a magical linear algebra thing, wherein if you have a function defined parametrically, like x. You want me to not talk about this, David?
Well, because it's like you're saying like parametric, and I know what that means, but I don't know if Ethnish knows what that means.
What do you mean,
Like,
like
yeah,
a function defined parametrically? Like what? Because like again, like I'm thinking, like aren't all functions?
Give me literally 30 seconds, David, and then cut me off, okay?
Sure, 30 seconds.
I think it's such an easy idea, actually. So okay, one way to define a function is say you want to define something in 2D. You can say x of t comma a vector x of t comma y of t, and you can define any relation that way. You can define something that will travel anywhere over space over time. It's like a particle moving in space and in space over time. Now let's say you want to say you just decide to, and it'll go in curly Q's, it'll zigzag. Now say you take the derivative of the first element of that and you take the derivative of the second element of that. So your initial function was x of t comma y of t. Now you've got dx of t comma dy of t. That thing is going to be the slope instantaneously at any point in time, okay? And it's going to be tangent to your curve, okay? So that's a gradient operation in 2 dimensions.
Okay.
Yeah.
So the gradient operation in 2 dimensions is just, so it's when you like apply the derivative operator to
Element-wise.
both functions. Okay.
Right. You apply element-wise derivative operator, and you can do it in 3 dimensions, 4 dimensions. And the really cool relationship of this, the unexpected consequence, is if you do this in say 3 dimensions, the gradient operator will always point in the direction of like maximum downhill.
Really?
That's where gradient descents come from.
Absolutely, it's absolutely surprising to me. It's completely surprising. It's a guarantee it'll always point in the direction. It's either maximum uphill or downhill. I don't remember which way.
I think it's uphill, but you can always just add a negative sign and then it goes downhill. So
okay, so question. So okay, how the heck is the gradient operator, which takes like a vector in, like, say R3 and returns a vector in R3? How is that a how does that work? How is a gradient a covector?
that one I'm not sure of.
Yeah, wait, because that's R3 then, that's not R.
Okay, question. Is the derivative operator alone a covector? Because that also doesn't do it. I see how in an indefinite integral, that's not a covector either, but a definite integral is.
I think the derivative is a linear map.
The derivative, yeah. So no. So in that case, the derivative. So like if we're talking about like our vector space of polynomials, right, that we were talking about earlier, then the derivative operator is not a covector. It's just the vector, because it takes one linear. So because it takes like one vector and spits out another vector, right?
Mhm.
But the integral is a covector.